Alrighty then. Just to answer your question as to where those degrees are from, the bachelor's and master's are from Wisconsin, and then I came out to California and got a PhD out here. It was working in Mexico, but that's another story. We have a lot of slides, so we'll just jump right along on this as soon as I figure out how to operate it. There we go. Geological aspects, speaking of geology in a large, very large definition as the study of the Earth, into topographic constraints on the road. Let's see, can I get that little guy to move? No, I can't get the arrow to move either. There it is. Hi. Topographic constraints on the road, water and its constraints on the road, and Drew's done a pretty good job of addressing that. I wish he'd written my presentation, but you'll get what you get. And then geology proper, where we're talking about soils and rock. I want to mention Mike Fuller, another senior engineering geologist with the California Geological Survey, from whom I've drawn a lot of this presentation. The presentation was originally prepared by myself for Trinity County, and then a couple of other people, including Mike Fuller, had adapted it for further work, working with Richard Harris, and I've kind of kludged that stuff together in this presentation. And Mike brought this in, that road design can be adjusted for environmental constraints, meaning that good road design can compensate for some pretty difficult conditions, but you can take good environmental conditions and with poor road design screw up a pretty darn good road otherwise. And good road design can be summarized as to keep the road grades, that is the angle of the road surface as you go up or down the hill with it, less than about 10%, and I'll explain what that means, because it makes it a lot easier to deal with and you don't have as much erosion issues. And then keep the road hydrologically invisible. Ideally, it shouldn't be intercepting water like Drew talked about, shouldn't be concentrating water in inside ditch, dumping it in another drainage, and so on. So if you do that, the road becomes much less of an issue on the landscape. A very quick discussion of percentage. It's a simple way to show the kind of the angle. What we do is we take the rise over a certain length. Let's say this is 10 feet and this is 100 feet. 10 divided by 100, blah, blah, times 100, it gives you 10%. And this shows to scale, as done by Mike Fuller, a 10% road, or a 10% side slope, pardon me, that's a road being constructed along it, a 30% side slope, and a 65% side slope. So you have, that's what we mean by percentage. It's a real simple way to talk about slope angle. Oops, sorry. And let me move that off to the side. Thank you. So in terms of topography and slope angle in particular, slopes that are steeper than 40% and really horizontal, and I'll explain that, horizontal in case you have water there, because you can't drain it when it's really flat, are difficult. Ideally, you want to have a little bit of a cross slope angle to help the water, give you some place to get the water to go. And the gentle slopes allow you to minimize road grade, excavation and fill volumes when you do road construction. And examples of this are toe slopes, topographic benches, ridges, and hilltops, pardon me. Here's a picture. This is from a document, and I've got several other pictures in here called Low Maintenance Roads that's put out by Wildland Solutions. And this just shows the flat slopes, which are difficult if you've got water there. Steeper slopes, and you can build roads on these. It just costs money, and it takes longer. And then the toe slopes and more gentle slopes where you can get the water off quite easily. With my cursor on my computer, which I can see and I think you can't, and I have to really use this little green arrow that is not being tractable for me here. If I click, there it is. Yeah, all right. We'll point with that in the future. So the gentle slopes minimize the road grade, the steepness, which that reduces the potential for erosion of the roadbed and stream diversion at watercourse crossings that Drew talked about, while allowing the road surface to drain down slope. Here, for example, is a really steep road grade that it's a power line road grade. And you guys know how the power lines just go straight lines up and over across the hills and ridges and stuff. And because they have a narrow, relatively small right-of-way typically, the roads they use to service those follow those along. This is out behind, not within walkable distance of my house, out in West Reading, and shows what happens when you don't get the water off the road, and it's steep. And if you have a road that's climbing through a water course crossing, unless you have that critical dip or the diversion prevention dip, the DPD, I think, that's a new term for me too, Drew. Unless you have these critical dips, then there's the potential for the water to be diverted down the road, where it will continue down the road until it actually comes off across the fill slope and erodes the fill slope. Sometimes it will continue down the road quite a long ways, especially if the road is insloped and it follows the ditch, and can erode a tremendous amount of road. Ideally, what we would like to do is to have the road come into the crossing and dip into the crossing and then dip out of the crossing, and actually at where the crossing is itself have a little dip here too to help that water, should the culvert plug, to help the water then go across and come right back down into the stream drainage. So we don't have this high diversion potential, which can pretty much give you really expensive road failure that you'd have to clean up. This is just an example of of an abysmal road, actually, where you can't use this until the darn thing dries out. And that could be, if they're lucky, a week, a year from the way it looks here. Another example, and this is from the Low Maintenance Roads pamphlet by Wildland Solutions, this shows a road that comes down here, swoops around this way, and as it does this, it picks up a water course here that follows the road until it kicks out at this point. And their solution for this is to very simply take that road, bring it up on the toe slope here, and run it across up here and outslope it, so any water coming down goes across the road, and this 4% here speaks to the percentage of outsloping of the road. And so that's one way you can deal with this. Get it out of the flat bottoms where the water is. Another thing about gentle side slopes is that they minimize excavation and fill during road construction. This results in shorter and potentially less steep cut slopes and fill slopes. And then since the potential for cut slope and fill slope failure increases with height, a correspondingly less likelihood of a cut slope or fill slope failure. Here's an example that was put together by Mike Fuller, and shows, let's see, with a really low cut slope, that's a 10%. It's got a low angle slope, a 3/4 and a foot cut and a 1/2 foot fill. And if he'd actually put this if he'd done equal amounts of fill and equal amounts of cut, those two slopes would have been pretty much equal. And you can see how the cut slope and fill slope depths increase as the slope angle increases. And then once we get above about 65% slope, we no longer find it practical to have a fill slope like this out here, because now you're about at the angle of repose, and it's really hard for this stuff to stay on the hill unless you use specific construction techniques that involve like cutting a little platform here that you then compact the fill up upon. Correspondingly then, what you need to do is that you have to haul this material away, and so that increases the expense of road construction on steep slopes quite a bit. So this shows what happens with high cuts. The potential for failure increases as the height of the cut slope increases or the height of the fill slope increases. And these failures then, like a cut slope failure, if you have an inside ditch, it'll block that ditch, keep it from draining, spill out onto the roadway, make it difficult to drive. Fill slope failure, of course, can actually take the roadway away making either of these can make the road impassable, and either of these can also end up in dumping a bunch of sediment into the downslope watercourse, which nowadays with the salmonids could be problematic. A question I noticed from Sally here is all the cut fill slopes show a flat cross slope of the road. Is that the goal? That is not the goal, but the goal of that particular illustration was just to show the differences in cut slope heights with different slope angles. We'd prefer to have outsloped roads a little bit, say 3 to 5%, versus other types of road construction, assuming that site conditions allow that, because they drain better, you have shorter cut slopes, and less spoils from excavation. If you compare outsloped road to an insloped road with a ditch, the cut slope would tend to be about 1/3 shorter, and the spoils are less than 50%. Left those tables out of this. This shows an illustration illustrating that. And so here's a road with a 12-foot, both of these have 12-foot running surfaces. This one's inslope to a 3-foot ditch. This one's outsloped. And you can see how much shorter the cut slope is, and then the cross-sectional area of these two different types of road constructions are going to be proportional to the amount of fill that would be removed when these would be constructed across this slope. So outsloping, here we go, saves you a lot on construction, and also gives you less likelihood that the cut slope is going to fail. Now we're going to step to the next subject, which is streams and wet areas, water in general. And we're going to address this. I'll try not to duplicate what Drew has done. There'll be a little bit of that, but some of that will be complementary to what he has spoken, what he has said. And we'll try not to duplicate too much. Just generally, in terms of environmental consequences, with roads, it's best to stay away from streams except to cross them. And I'm not going to address stream crossings any more than I already did above when I talked about the potential for diversion. Pete Cafferata is going to address the stream crossings when he does his presentation on July 2nd. We'll talk about road effects on the streams and stream effects on the roads. Roads can increase the sediment discharge to streams. I'll get that over here. And it can increase stream peak flow, as Drew spoke about. And these road effects, these negative road effects, can be reduced by increasing the difference between the road and stream, enhancing what we call buffer effects. Here's a diagram that just shows how roads interact with streams, how they can be connected. The diagram that Drew showed is very good as well. This assumes an insloped road, which is not our preference, but all the runoff from the road surface, the impermeable road surface, will tend to run into the inside ditch and then be concentrated all along that area and then kicked out with a ditch relief culvert and then run down towards the stream. The farther the road is away from the stream, the more opportunity there is for this water coming out of here to infiltrate into the buffer and deposit its sediment. The closer to the stream, the more likely will be that the water that's being kicked out by these ditch relief culverts will actually get to the stream and bring in its load of sediment, or at least some of that. And the amount of water that's done by each of these ditch relief streams can be minimized by increasing the frequency with which these are installed. I should stop talking about this because Don Lindsay is going to be talking about road drainage also on July 2nd, and so I don't want to take away too much of that. The other thing, when you have a road close by, you sometimes have failures of the fill slopes. If you're close to the stream, those failed fill slopes can reach the stream and deliver a large slug of sediment directly. Lastly, runoff from the road itself can go into the ditch close to the water course this is a water course crossing here, close to this water course crossing, and deliver directly to that water course, which then delivers it to the main stream. Flows, peak flows can be increased. Drew spoke about that. Excuse me. That little green arrow I hope won't bug you guys too much. I'll try to keep it controlled. These are increased by runoff from the compacted road surface, cut slope, and the fill slope, and interception of shallow groundwater by the cut slope. This is, Richard told me this is a really, really busy diagram, and it is. But I wanted to mention how subsurface water comes off the hill slopes. It not only percolates straight down to the groundwater table, but as the water percolates down, it encounters increasingly less permeable. Layers, and as it reaches those less permeable layers, it tends to pond up on top of them and then move down slope like that. That's what Drew called subsurface storm flow, and on this particular diagram they call this through flow. Okay, and that's all I really want to mention from this. When a road is constructed on steep slopes, however, the cut slope can encounter the water table or this shallow subsurface storm flow and bring that to the surface. And Drew spoke about how much more quickly that water, which is intercepted, will get to the stream, enhancing both the peak flow and the timing of the peak flow than it would if it had flowed directly through the subsurface routes. Here's an example from west of Redding on a little hike I and my wife were taking between Redding and Old Shasta, and this is a road cut here, and here we've got, it's been raining earlier that week, we've got water running down the ditch, and right there, let me go back a moment, these are called soil pipes, and these are larger macro pores that from tree roots, could be from gopher holes and so on, that water also flows down through besides just perking along through the soil. Okay, and what's happened here is sorry I didn't use the arrow, what's happened here, here's a macro pore that's been intercepted and the water's running right into the ditch here. And if we look carefully, or at least to my eye, and maybe it looks saturated along the edge here, and so you're getting saturated flow into this ditch as well as the flow right out of the macro pore. So anyway, we can minimize this interception of shallow groundwater by smaller ground width and road width, and by outsloping, which eliminates the inner ditch and narrows the road width and raises the inside edge of the road. And here's that same diagram you saw earlier, showing here's a water table, or we can consider this maybe one of the flow routes where the subsurface flow is taking place down here. And by using the insloped road, we avoid intercepting that, whereas the outsloped road, whereas the insloped road intercepts that and is going to be taking a lot of that water out of the system onto the surface and then down. Turning to stream effects on roads, we're going to discuss inner gorges briefly. And inner gorges are those areas along streams that are incising where you have the really steep slopes directly adjacent to the stream. This occurs most commonly in areas that are uplifting, like the Coast Range, and the streams are eroding to keep, trying to keep down to base level. And these inner gorges are formed by landsliding as the streams take away the support at the toe. And they're a poor location for roads because they're unstable and they're too close anyway. Also, roads that are near the valley bottom are going to have to cross any tributary streams that come into the main stream. This means you have to install a water course crossing, and once you've installed it, then you're going to have to take care of it. Water course crossings are kind of like children. You know, once you have them, they're your child forever, and they're going to have to be maintained. Lastly, what happened? Just a minute. I'm having an issue here with my computer. Let me bring that back up. There we go. Thank you. Lastly, The idea is, let me get that arrow out of here. This is over in the Coast Range. This is actually the toe of a big deep-seated landslide that's being eroded by the stream. And then as the stream takes the toe away, we get debris slides down like so. This is a very, very bad place to want to construct to construct a road. You want to find some other place to construct this. Notwithstanding that this is a state highway on the other side, but this actually isn't the side that the landslide's coming in on. Some diagrams. These are from Oregon Forest Resources Institute in 2002. This shows a road that has been run right up this drainage way, and here you've got a crossing here, crossing here, crossing here. To construct, but they have to be maintained. Mike Fuller suggests that this is destined for disaster, and shows Highway 50 to Lake Tahoe being an excellent example. Now, if we move it out of the streamway and bring it up on the slope, this is better. Now, you can have issues with steep slopes and the construction issues on the steep slopes, and also the issues of intercepting tributary streams. I don't see any particular here, but you could certainly have one in the swale and potentially one here. So there's still more watercourse crossings than if you had it higher up on the slope. And the other issue is that streams tend to erode along the outside corners of their bends, and if that erosion continues and you have the road is too close, the stream can actually undercut the road, as we see in this example here, where this is a road a failure that's caused by stream undercutting. And clearly this road, I mean, because it's failing from being too close to the stream, is too close to the stream. So ideally, if it allows you, and mind you, many roads will not, because the points you're trying to connect just don't allow for this, or the ridge tops are inappropriate. Best to try to get the roads higher up on the hill, on a ridge top if possible, but the farther up you get, the less you have the potential to interact with tributary streams, for example. And here's an example from the Oregon Forest Resources Institute. And examples that you may be familiar with in the Sierras, for example, is Highway 20 east of Nevada City, or I-80 once it gets up on top of the ridge is similar. So stream effects on the roads. With watercourse crossings, I've already discussed these. They're not only the aspects of installing and maintaining them, but also the failure potential is another issue. Pete Caffrad is going to discuss those. And just if you can avoid streams and avoid watercourse crossings, you're best off. But clearly there are times when you have to do that, and then you just do the best you can. And Pete will discuss how to construct those, how to address the issues that are associated with watercourse crossings. And lastly, with water, we want to talk about wet areas. How do you identify those? Well, clearly if you've got water standing on the ground surface, that's pretty straightforward. Less clear are water-loving plants. Once you identify those, you will understand that there are certain plants that suggest that you have shallow water around. These include horsetail, sometimes called equisetum, maple, dogwood, blackberry bushes sometimes, hydrophytes, water-loving plants, and green areas when everything else is dried up. Problems associated with this, with wet areas, there's surface drainage across the road and the tracking of sediment to streams, seepage into the road prism itself. Don Lindsay, my associate here in Reading, is going to address road drainage. He'll talk about road design, how to avoid this, how to get the water off the road. He will be speaking along with Pete on July 2nd. But I'm going to mention one thing here is that say you've got water and as a result of that, you've got soft soils and road substrate. One of the issues that can occur there is rutting, which will tend to concentrate any surface water down the road and tend to erode it. Well, how can you deal with that if you've got a situation where you've got soft soil and road substrate? Well, first of all, we want to try to avoid that, but we have existing roads that have wet areas, and sometimes even in designing a new road, you have to go through an area, and it's just the way it works out. Don, you can drain these. Don will talk about that. If you can't drain them, you can use geotextile as a separator. And what this is a material that allows you to separate fine material from the coarser material and keeps it from pumping down into it. If you don't use this, you can take and throw all the gravel you want to on some of the soft road, and you drive over that a number of times, and that gravel gets driven down into that, and it just keeps disappearing and can become kind of a gravel sink. The use of geotextile will allow you to separate these so the gravel no longer gets driven down into the fine, soft material below, and use a relatively small amount of road base and have a pretty decent road. Here's an example of this being done where there's a relatively soft road grade here. This is geotextile that's being spread out. The geotextile is permeable, allows water to go through it, but is sufficiently fine, the pores are sufficiently fine that it will keep the fine material from being squished up into this road base when people drive over it. I've seen pictures of this actually being used like on a marsh. I don't think that was for a permanent, well, I really don't know, but they were going to use that for hauling across. This is the time, Richard, that we want to take a little break for questions in the middle. We cover a lot of them, but there are things that we're just not going to be able to address. But we'll do what we can. Come on, there we go. This is a generalized geologic map of California. And for those of you that can see this large enough, there's a geologic time scale over here, which ties in with those eras or periods: Quaternary, Tertiary, Mesozoic, Paleozoic, and Precambrian are reflected over here in this description of the rock units. The things that you notice right away is this the Great Valley, Sacramento River Valley, which is filled with Quaternary sedimentary deposits. And the Quaternary is the stuff back to about 1.6 million years ago. And you can see this is just the sediments, the gravel sands, and so on that deposit in the low areas where you've got valleys. There are other sedimentary rocks and tertiary ones that go back to about the age of the dinosaurs, back to 65 million years ago. These brown ones out here in the Coast Range, and the green guys are the Mesozoic. These were deposited during the age of the dinosaurs, and they're out here in the Coast Ranges. The other major issues you see here, I'm going to move to the next slide here, is that we've divided the California up into 13 different geomorphic provinces, and the major ones, here's the Great Valley, you've seen that, the Coast Ranges, north and south, Klamath Mountains, Cascade Range, and Modoc Plateau. If you look at both of these both are tertiary to quaternary volcanic rocks, includes Mount Shasta, Lassen Peak, and the basalt lands out here in the Modoc Plateau. The Sierra Nevada, this red stuff is all granitic rocks. This blue tends to be, I think that's Mesozoic and Paleozoic sedimentary rocks, and the Mojave Desert, Transverse Ranges, Peninsula Ranges. We're going to be mostly we'll be talking about, when we talk about landslides, will be the North Coast Ranges, the Klamath, and the Sierra Nevada. There's a tremendous amount of geologic information that's available through the mothership site, the California Geological Survey site, at this URL. or you can just Google it on the internet. It's the CGS, the California Geological Survey, is part of the Department of Conservation, hence that's why it says conservation here, /CGS and so on. So if you want more information, want to see what's available in geologic maps and so on, please feel free to drill down into the CGS site. The issues that we're going to talk about that results in geology, mostly we'll talk about unstable soils and landslides, a little bit on rock slides, rockfall, very little. We'll talk about erodible soils and asbestos-bearing rock units, because the asbestos in those rock units can be problematic health-wise. Unstable area characteristics. For unstable areas that are active, there are tension cracks, head wall scarps, leaning, jackstraw or split trees. Jackstraw are just trees that are leaning all different directions. Trees with excessive sweep, that's trees that the underlying soil has been rotated with respect to horizontal. The trees tend to grow, at least conifers tend to grow vertically, so they will keep turning vertical, and you get these stems that have that sweep from non-vertical up to a vertical. Evidence of impaired groundwater movement. Because of sliding, you get impermeable layers from clay smearing along the slides, and the surface tends to be displaced, so we can get sag ponds, springs, patches of wet ground, and the vegetation that goes with it, and correspondingly short irregular surface drainages that just start at a spring and then soak back into the ground farther down instead of forming continuous streams. Because of this, you often the streams may just run along the surface rather than have eroded themselves good valleys. Because of displacement of the Earth's surface by land movement, we get what's called hummocky topography, which is kind of rolling, bumpy ground that has topographic benches and closed depressions on it. Here's an example of active slide where you have a fresh headscarp and intermediate scarps that are unvegetated. Here's tension cracks up at the top of it. Trees that have been knocked down. There isn't many trees on this, otherwise we wouldn't be able to show you the other features. Tilted trees. And then after the slide has settled down, has stopped moving, it's in between moving, what we call dormant. It hasn't moved for at least a year. And as time goes on, these scarps tend to get vegetated. They tend to get rounded because of surface movement of soil creep and so on. And so the signs of it being an unstable area become muted. But you can still see here is the hummocky topography. Here's a closed depression. But the trees that have grown up here subsequently are all vertical. This is an example of a small active slide above a road cut in Trinity County. And what you can see here's some tilted trees, jackstraw trees really. These are falling off of the scarp. This is the head scarp here. And these reflect back tilting. Example of a small active slide above a road cut in Trinity County. And what you can see here's some tilted trees, jackstraw trees really. These are falling off of the scarp. This is the head scarp here. And these reflect back tilting of this slide mass in here. So this isn't the world's best picture of one. Mike had one, which I don't know where this is from, I apologize, but it isn't covered with trees, so you can see this quite well. Here's a former paved surface, which has been down-dropped like 15, 20 feet and kind of broken up here. This whole slide mass appears to be down-dropping and moving towards this drainage that is hidden back out in here. Here is an example of an older slide, a dormant slide that was down-dropped. Here's the top of the slide right here, okay? The top of the slide mass. this part of it is failing into the water course through debris flows, debris slides. Here's another debris slide over here on the far side. This is a pretty active area, wherever this is. I apologize, I don't know. This shows arc-shaped cracks in side cast fill, and this suggests this road is in trouble. Basically, you often see this on paved roads where they have taken tar and tarred in the pavement, and sometimes there's new pavement here because this is downset, and so they just pave it over and keep the road level up to the same. If it's just a simple linear crack, there's often settling of the fill, and that's all that ever happens. Just a little crack, and once that's graded, you never see it again. But when you see the arcuate cracks, that suggests that there's a lot more that has the potential of occurring in this case. There are two major types of unstable areas that we consider. One is the end members are deep-seated landslides, which tend to be rotational. They tend to be composed of clay-rich soils that are cohesive because they're clay-rich, that is, they'll tend to stick together. And so deep-seated means it has a relatively thick slide body. Sometimes includes bedrock. On the other hand, there are what are called shallow-seated landslides, and these include the debris slides, the debris flows, debris torrents, and these are non-cohesive, like sand and gravel. And often you consider them as like the regolith over bedrock, and it's a relatively thin body compared to the slide area. There's a classic example of a deep-seated landslide. This is the landslide at La Conchita, which is lies between Santa Barbara to the west and Ventura to the east on the south coast of California. And this is the failure that occurred in 2005, I think. There was an earlier failure in 1995, and a much earlier failure that you can see from up here. Some suggestions were that it may have been caused by, may have been exacerbated by irrigation from a orchard that's up above. Contrast, here's a shallow-seated landslide. This is a debris slide that came off of the east slope of Bully Chute Mountain in Trinity County. And investigations by one of my colleagues back in, I think it was 1998 when he looked at this, suggested that this was just natural in origin, that its occurrence had nothing to do with the road that goes across it here. And this failed. Down in here formed a debris torrent that went down into Indian Creek and then flowed out, 10, 12 miles all the way to the Trinity River to the north. And for those of you with that are used to looking at this, there's another little debris path that goes right down through here. You can see where the trees have taken this, or taken out along this drainage. So these are shallow-seated landslides and debris torrent tracks and so on that result from them. The shallow-seated slides often are headed in what we call colluvial hollows. And what these are hollows in the bedrock. You may not see them so much at the surface of the earth. And when we get these get full enough and we have a storm that has enough water that we can actually get positive pore pressures down in here that may, through buoyancy effects, support this material enough that the friction that tends to hold it in place is diminished, these can discharge, like you saw in the previous picture. Once that occurs, these will tend to fill up again through soil creep and tree throw, rodent, gopher is kicking soil down slope. Truly, that is more of an effect than one might think, until it's poised again for the next opportunity. And the recurrence interval on these is anywhere, it depends where you are, where it is, but can range from a few hundred years to tens of thousands of years. Here's an example of one that occurred in 1982 above the town of Pacifica. And here you have a colluvial hollow, and it discharged and comes down at this is a steep slope, at quite a high rate of speed. There used to be a house here, maybe two, and there used to be people living in them who were killed actually by this feat of nature. But you know, sufficient understanding of what was upslope of these could have resulted in limiting where people built their houses here. I mean, you have another colluvial hollow here, and you got another one here. Bingo. And so, okay, anyway, enough of that. So, unstable areas typically are associated with steep slopes, which in California occur mainly from tectonic uplift and mountain building, and then you have subsequent erosion and valley incision. And then water. And what the water does, that tends to weaken the substrate, and through buoyancy effects can reduce slide-resisting forces. And then you combine that with cautious rocks. You just can't see the micas, they're too small. And serpentine, our state rock. High permeability rocks over low permeability rocks. For example, the andesitic material that filled the valleys in the Sierras and now exist as high plateaus. These are very permeable, and when the water perks down through them towards the bedrock, there you have an opportunity for slides along those. And fault zones. Fault zones aren't as important because they're not as widely distributed as some of these other rocks. Bad areas in particular are those where we have areas of groundwater convergence, such as the bottoms of swales or colluvial hollows, and areas of groundwater discharge, like at the toes of slopes, intergorges. This, we have a technical difficulty here. On the right side of this was supposed to be a slide that shows the annual rainfall in California, but I will tell you what, this doesn't show up. We're learning new things here. So in the north, rainfall is highest in the Coast Ranges and in the Klamath Mountains and in the Sierra Nevada, and then behind these we have rain shadows. So we have a lot of landsliding in these areas because of the water combined with the rocks. We have some landsliding down below here in these areas from summer storms, but not nearly as much as we have up in here. And this is just comparing and showing again the geology. So moving along, Richard is telling me I've got not a lot of time left, so we'll move right along here. Examples of rocks in California associated with unstable areas. The mixture rocks, melange rocks, that includes the Franciscan Formation and the Coast Ranges. Ultramafic rocks, which include serpentine, and then the volcanic mudflow cap over less permeable granites, and metamorphic bedrock in the Sierras. So for unstable areas, try to avoid them if at all possible. If you know, sometimes you have to put a road there. Sometimes you've got roads there, and you just deal with them as best you can. Do not, if you can, avoid it. Do not excavate the toe of a landslide because that reduces the landslide resisting forces. Don't put material on the head that increases the slide driving forces. And don't concentrate water onto or into the slide. And if you have to deal with them, you may want to find it necessary and appropriate to hire a state-certified geologist to help you out with that. Rock slides, very briefly. With sedimentary rocks, you have beds like this of different types of rocks. In metamorphic rocks, there's something called foliation, which imitates bedding. Rocks tend to be broken, what we call joints that are just planar structures in the rocks. If these are tilted, they can form unstable areas when the tilts are parallel, when the tilting is parallel to the slope or steeper than the slope. If the bedding tilts into the slope, that's stable. If it's horizontal, that's stable. erodible soils, DG soils, sandy and silty soils, especially DG. We won't talk about them a lot, but when granite weathers, it weathers from this igneous rock. When these little black things in it, the biotite break up, they expand and tend to break the rock up. And you can end up with a sand or silty soil that's extremely erodible. And Drew showed excellent pictures of those, of a road that was eroded in that. I wish I had that picture in this presentation. Drew also pointed out to me this particular graph, which is from the Washington Road Surface Erosion Model publication. And these shows the erosion rates on different types of road surfaces based on the underlying type of rock. And the granite soils stand out head and shoulders above everything else except tuff. And tuff soils, which are a volcanic soil, are not typically as widespread in California as the granite. And these are eroding at, what, about 20 tons per acre per year. Much more erodible than the others. The decomposed granite soils we have are found mainly where the granites are, in the Sierras, to a lesser, and down here in the peninsular ranges. And then we see plutons that are out here in the western Sierras and in the Klamath, and there are some isolated plutons. That's these red rocks, okay? That's the red rocks that are down here in the coast ranges. These are not so much of an issue in the higher Sierra, where the soils have been removed by glaciation, but more of an issue where they haven't been glaciated and you have deeply weathered granitic rocks, or the granitic glacial deposits are also an issue. How to identify these soils? There are a bunch of field tests for soil textures that I really don't have a chance to go through. You can get soil survey data from the Natural Resources Conservation, and the S escapes me, and from the U.S. Forest Service. And these can also tell you about the suitability of soils for road building and other uses. So I highly recommend soil surveys for areas where you're planning on doing something, constructing roads. Mitigating these erodible soils, keep the road gradients gentle. Get the water off the road. And this is what, outslope it, water breaks. Donnelly will talk about that. Rock it. By that, what we mean is put gravel on it or pave it, something like that, to keep the water away from the really erodible soils. And then CAL FIRE has a guidance document which is available on the internet at this URL. That's www. I'm not going to read it. You'll be able to access this later, and we'll also, and this guidance document is recommended mitigation measures for timber ops and decomposed granite soils. And lastly, hazardous asbestos dust can be derived from asbestos-bearing rock units. And if you construct roads in them, and actually if you use those roads when they're dry, you'll have dust coming up that can contribute to respiratory issues. These occur in ultramafic rocks and soils. They've been a big problem in El Dorado County. You can identify these from geologic maps, rock descriptions. There's a CGS site at this URL that, and you can Google this, that gives you lots of information on those. And all you really need to do is keep the soil damp. Now, you're not going to do that all summer, but if you're doing road construction on these, that's easy enough to do. Those ultramafic rocks on this map are these purple guys, the serpentinized ultramafic rocks. The biggest of these are up here in the, I've lost the Klamath Mountains. There we go. That's a Trinity ultramafic sheet there. And there's some more exposed here and in the northern Sierras. And there's some little pods also that are out here in the coast range.